Okay, folks, it's that time of the morning, so I'm going to go ahead and get started. People may still pop on, but I'm going to get into material. The first thing I'm going to be doing today is we will discuss covalent molecules and we will discuss acids. This will finish up the section on how to name chemical compounds and how to write the formula for chemical compounds. I expect that to be at least 20 to 40 points of the next exam. After that, we will get into Lewis structures, which will basically be where we'll talk about an expanded octet, a formal charge, and multiple central atoms. Then we'll get into PR theory, where we'll talk about electron geometry, molecular geometry, and bond angles. So this is the plan for today. I expect us to be here most of the time today. I will give breaks like I did last week during the process, however, so that you can take a break here and there. Now, essentially what we're doing today, folks, is this first part with the covalent molecules and acid is finishing up our discussion about formulas and names. We've talked about the polyatomic, well, we've talked about monoatomic ions. These are ions from the periodic table. We've talked about polyatomic ions. And yesterday, we talked about how these ions combine to form inorganic compounds through an electrostatic attraction, and specifically ionic compounds. And we talked about how to write the formulas of those ionic compounds and how to name the ionic compounds. Then yesterday, we started talking about covalent molecules, and we talked about the diatomic elements, and we talked about hydrogen with group 15 through 17. Again, when talking about those two categories, we talked about how to get the formula of those compounds and how to name those compounds. This first portion where we're dealing with the covalent molecules and acids is going to be completing that story where we're naming and developing the formulas for the different types of molecules that we will be discussing throughout the entire semester. I expect at that point to take a break and then come back and do Lewis structures. Now, this Lewis structure portion is going to be completing the story that we started last Thursday, where we started talking about electron dot configurations, and we developed Lewis structures for ionic compounds, and we started discussing Lewis structures for covalent molecules. Again, the second portion of today is going to finish that story where we talk about Lewis structures for molecules that have an expanded octet. And as we talk about the expanded octet, we'll get into formal charge. And then we'll also talk about Lewis structures where there are multiple central atoms and how to essentially read a molecule with multiple central atoms. Finally, during the last portion, we're going to start getting into VSEPR theory, which will be the newest conversation. And so, but VSEPR theory is based on Lewis structures. So if you don't have a solid foundation of Lewis structures, you're not going to be able to do VSEPR theory because they are based off of the Lewis structure. As with last week, I will have the chat up. So at any point, if you have a question, you can either unmute yourself and ask the question, or you can place the question in chat and I will keep an eye on chat. So any questions before I get started into the information? Okay. So yesterday, we started a discussion of covalent molecules. Covalent molecules have a covalent bond. The covalent bond arises through the sharing of electrons between two atomic nuclei. You can recognize that you're working with a covalent molecule because the elements within the compound will either be nonmetals or metalloids. There were 4 categories of covalent molecules that I wanted to discuss. The very first was the diatomic elements, which are Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These elements, when they are found in nature, all by their little lonesome, always comes in pairs. So the oxygen you breathe is actually O2. And to name diatomic elements, you simply name the element. So O2 is called oxygen. Br2 is called bromine. The second category we talked about is hydrogen with group 15 through 17 nonmetals. The number of hydrogens that are in the molecule is going to be equivalent to the charge on the group 15 through 17 nonmetal. And so, for instance, phosphorus carries a -3 charge. Therefore, a compound that contains hydrogen and phosphorus is going to have 3 hydrogens and 1 phosphorus. To name these compounds, we name the hydrogen and we name the other element with the ending IDE. So the example of H3P is hydrogen phosphide. That is true for every single compound of hydrogen with a group 15 through 17 nonmetal except for H2O. And there is only one name I will accept for H2O, and that is water. So we've discussed the diatomics. We've discussed hydrogen with groups 15 through 17. Today, we're going to discuss alkanes and then binary covalent molecules. So alkanes. Alkanes are the simplest of all organic molecules. They are compounds that contain carbon and hydrogen only. Alkanes consist of single bonds only. So there are no double bonds in an alkane. It's going to be all single bonds. And they have the generic formula of C subscript N, H subscript 2N plus 2. So if we have 1 carbon, it would be 1 carbon, and the hydrogen would be 2 times 1 plus 2, or in other words, we're looking at CH4. For 2 carbons, the formula would have 2 carbons, and it would be H2 times 2 plus 2, or in other words, it's C2H6. Notice something that I mentioned yesterday. Covalent molecules, the formulas are not simplified. In other words, we're not going to change C2H6 to be a simplified formula. Its molecular formula is C2H6. For the next one, if we're talking 3 carbons, then the number of hydrogens is 2 times 3 plus 2. Or in other words, it's going to be C3H8. 4 carbons, if you do the math, will be C4H10. 5 carbons will be C5H12. 6 carbons will be C6 1920x1440. 7 carbons will be C7. H16. 8 carbons, C8, H18. 9 carbons, C9, H20, and 10 carbons, C10, H22. I will not go past 10 carbons for this class. Now, naming these. One thing that you're going to note when I name them is that I'm going to, or I should say all of them are going to end in A and E. That A and E tells us that it is an alkane, and therefore it's carbon and hydrogen only, and therefore it's going to be single bonds only. If the ending is anything other than A and E, then it changes the identity of the type of compound we're working with. Now, the first 4 you're just going to have to know, but they are important. CH4 is called methane. Methane is the gas that is given off by a variety of things, but one of them is going to be flatulence of animals. C2H6 is called ethane. C3H8 is important. It is the gas that is used to heat homes. It is called propane. C4H10 is also an important gas. It is the gas that is used in a lighter fluid. So it is butane. Once you get past butane, it actually becomes easy to name them because the prefix of the compound is going to be related to the geometric shape. It is going to be related to a geometric shape. So, for example, there are 5 carbons in the next compound. A 5-sided structure is called a pentagon. Well, a 5-carbon alkane is called pentane. The next one, C6H14, there are 6 carbons. A 6-sided structure is called a hexagon. Well, a 6-carbon alkane is called hexane. The next one has 7 carbons. A 7-sided structure is called a heptagon. The 7-carbon alkane is called heptane. The next alkane, C8H18, is actually quite important to anybody that drives because it is associated with the gasoline that is put into a vehicle. And that is the gasoline octane. The next one is 9 carbons. The prefix for 9 is nona, so it's nonane. And finally, a 10-sided structure is called a decagon, while a 10-carbon alkane is called decane. So those are the alkanes that you must know. You must know their name, and their formula, and you must be prepared to go between the two on an exam. Questions about alkanes? Okay. For our purposes, these first three categories have a limited number of molecules that you need to know. The first category, the diatomic elements, there are 7 of them. You just have to know the 7. For hydrogen with group 15 through 17 nonmetals and metalloids, again, the number is limited. You just got to pretty much know what you're doing. For your alkanes, there are 10 that you have to know. The next category is going to be the largest category of covalent molecules. And these are called the binary covalent molecules. Bi means 2. So basically, binary covalent molecules are going to consist of 2 elements. Now, because we are talking about covalent molecules, and covalent molecules have covalent bonds, which arise through the sharing of electrons, what it means is that the same 2 elements can make multiple compounds. I've given you a couple of examples here. CO is carbon monoxide. CO2 is carbon dioxide. They consist of the same 2 elements, but these same 2 elements are in different ratio, is found in a different ratio. Or you can look at water, H2O, and hydrogen peroxide, H2O2. Again, it's the same 2 elements, but they are found in a different ratio. Now, no 2 compounds can have the same name. So we use a prefix system to indicate how many of each element is present when we are naming the compound. Now, with this prefix system, this is the same prefix system that you use for shapes, triangles, hexagons, stuff like that. It is the same prefix system as you use for shapes. Now, I want to warn you, prefix, and you may want to make a note of this. Star it. I don't know how you want to do it. The prefix system will only be used in alkanes and binary covalent molecules. The prefix system will only be used in alkanes and the binary covalent molecules. We do not use the prefix system for ionic compounds. We do not use the prefix system for our diatomic elements. We do not use the prefix system for hydrogen with group 15 through 17. We do not use the prefix system for acids, which we'll do here in a minute. You only use the prefix system for alkanes and binary covalent molecules. So the prefixes. Mono is used when there is only one. Now, we never use mono with the first element in a compound. We only use mono with the second element in the compound. Whereas once you get to 2 through 10, if there is multiples of the first element, you will use a prefix. And you will use a prefix on the second element. So again, mono is the oddball. It's only used on the second element. Otherwise, prefixes are used for the first element and the second element in a binary covalent molecule. Once again, you're only going to use this prefix system with alkanes, starting with 5 carbons, and binary covalent molecules. You will not use the prefix system with any other molecules. When you're using the prefix system, mono is only going to be used on the second element, but all of the rest of the prefixes will get used for this first and the second element if they have that quantity. So let's look at some examples. I gave you an example of CO and CO2. There is 1 carbon and 1 oxygen in the first compound, as represented by the subscripts associated with each element. We do not use the prefix mono on the first element, so this one is simply carbon, but we do use the prefix system for the second element, so this is monoxide. So CO is carbon monoxide. In my second example, there is 1 carbon and 2 oxygens. The prefix for 1 is mono, but we don't use mono on the first element. So again, this is carbon. And there is 2 of the second element, so it is dioxide. It's important. This prefix system is important because I want to know whether I'm breathing in carbon monoxide or carbon dioxide. Now, both of them can kill you, but they kill you differently. Carbon monoxide will actually replace the oxygen in your bloodstream. Carbon dioxide can simply make you suffocate. So they behave differently. Let's look at another set of examples. Let's look at SO3 and S2O3. We have 1 sulfur and 3 oxygens. The prefix for 1 is mono, which we don't use on the first element. So this is simply sulfur. The prefix for 3 is tri, so this is trioxide. So that is sulfur trioxide. Now, I actually like using this particular one because I want you to note the difference between sulfur trioxide and sulfite. Sulfite has a charge, whereas sulfur trioxide does not. Again, the polyatomic ion sulfite has a charge, where sulfur trioxide does not. And that is the difference between the two. Which basically what this difference means when you start looking at Lewis structures is sulfite has 2 more electrons that we have to work with than does sulfur trioxide. Sulfite has 2 more electrons that we have to put into the structure than does sulfur trioxide. Okay, the next compound has 2 sulfurs and 3 oxygens. The prefix for 2 is di. So this is disulfur. And the prefix for 3 is tri. So this is trioxide. So S2O3 is disulfur trioxide. Let's look at the next one. We have 2 nitrogens and 5 oxygens. 2 nitrogens is, the prefix for 2 is di, so that's going to be dinitrogen. And the prefix for 5 is penta, so that's going to be pentoxide. So dinitrogen pentoxide. In the last one, we have 4 phosphorus and 10 oxygens. The prefix for 4 is tetra, so that's tetra phosphorus. And the prefix for 10 is deca, so decaoxide or decoxide. So tetraphosphorus decoxide. One thing you will notice about these binary covalent molecules, the first element is simply given its name. The second element has the ending IDE. That's pretty much a common story, no matter whether we're dealing with ionic compounds or covalent molecules. The first element is given its name. The second element is given the ending IDE. Questions about how to name binary covalent molecules? Okay, then let's go to how to go from the names to the formulas. When you go from the names to the formulas, you are going to simply translate what is described. That's the beauty about binary covalent molecules. We flat out tell you what is in each one. So, nitrogen dioxide. Since there is no prefix, that means there's 1 nitrogen. And then the prefix 2 means dioxide, so 2 oxygens. So the the formula for nitrogen dioxide is NO2. The next one, we have the prefix di, meaning two, nitrogen, N, mon, which means one, oxide, oxygen. So the formula for that one is N2O. So literally, when you get to from the names to the formulas, you're simply going to translate it and then write it out. Questions about binary covalent molecules as a whole? To me, the binary covalent molecules should be the easiest. The biggest challenge is recognizing that you're dealing with a binary covalent molecule. So understanding that it is going to consist of two nonmetals or metalloids, and it is not a diatomic, it is not hydrogen with group 15 through 17, and it is not an alkane. So being able to recognize that you're dealing with a covalent molecule and it's not one of the first three means that it's a binary covalent molecule. Okay. Now what we're going to do is we're going to do the last category of formulas and names, and that is going to be to learn to deal with acids. There are multiple definitions that we could use for an acid, but the definition that we're going to be using is going to be the Arrhenius and the Bronsted-Lowry definition because they're identical. And the Arrhenius and Bronsted-Lowry definition says that an acid is a proton donor. The reason it's called a proton, look at the formula for a proton. It is simply H plus. That H plus means that we lost an electron from our hydrogen atom, and all that's left is the proton. So that's why it's called a proton donor, because all that's present is actually a proton. There's no electrons. We're specifically going to be dealing with inorganic acids. These are substances that, when dissolved in water, have an acidic hydrogen. Since we're talking about a substance dissolved in water, this substance is going to have the same matter of aqueous, AQ. Now, acids can come in, well, technically they can have more than this, but we can describe an acid by the number of hydrogens that are donated. When we're dealing with a monoprotic acid, we're talking about there being only one acidic hydrogen. An example of a monoprotic acid is going to be HCl aqueous or HC2H3O2 aqueous. These are examples of monoprotic acids. A diprotic acid is going to be a substance that can lose two acidic hydrogens. And a triprotic acid can lose three acidic hydrogens. Now, with the diprotic acid and the triprotic acid, this dissociation occurs in a stepwise fashion, meaning we're going to lose one hydrogen at a time. So let's just look at a couple of examples what we mean by these acids. Okay, HCl is an inorganic acid, so it is dissolved in water. Being an acid, it is going to be a proton donor, meaning that the hydrogen from the acid is going to be donated typically to the water. So the result is going to be the chloride that will be left over from the acid and hydronium, which is formed. One of the polyatomics that you were asked to memorize is hydronium. Hydronium is not typically going to be, we are not typically going to deal with hydronium in an ionic compound, but we are going to deal with hydronium when we talk about acid dissociations. So again, HCl is an inorganic acid, meaning that it is dissolved in water. Being an acid, it is going to dissociate and donate its proton to the other compound, in this case, water. So that what's left is the anion of the acid, and then it forms hydronium. H2SO4 is another example of an acid. It is going to donate its proton. What's left over is HSO4 minus, hydrogen sulfate, and hydronium. Now, H2SO4 has two acidic hydrogens. So it loses its acidic hydrogens in a stepwise fashion, meaning we are going to lose one at a time. So we lost only one of the acidic hydrogens in the first reaction. Now the second reaction can occur and a second acidic hydrogen can be donated to form SO4 2 minus and a second hydronium. At this point, we're about to get into how to name and write the formulas for acids. So before I do that, I want to ask, do you have any questions about what an acid is? Because that's what we've been focusing on at this point, is really the definition of an acid, specifically an inorganic acid. Okay, then let's get into the formula of an acid. When you look at HCl, when you look at H2SO4, when you look at HC2H3O2, one of the things that you will notice is that typically the acidic hydrogen gets listed first in the formula. Or if in the case of H2SO4 that had two acidic hydrogens, because it was diprotic, both of the acidic hydrogens got listed first in the formula. When we're developing the formula of an acid, the number of hydrogens is going to be equal to the charge on the anion. So for example, bromine. Bromine as an anion is Br minus. It has a -1 charge. So there is going to be 1 hydrogen in the acid. So the formula for the acid is HBr. And I always include aqueous to help distinguish it as an acid from the covalent molecule of hydrogen with a group 15 through 17. So a lot of times when I write acids, I'll always put aqueous behind them just to distinguish them between the covalent molecule and the acid. Another example is phosphate. Phosphate is PO4 3-. It's one of your polyatomics. So it has a -3 charge, which means it's going to have 3 hydrogens in the acid. So it is H3PO4. And again, I'm going to use aqueous just so that I can indicate that we are dealing with an acid. Now, it is the next part that you've got to be prepared to do, because you've got to be prepared to go between the name of the acid and the formula of the acid, and the formula of the acid back to the name. If the anion ends in IDE, then the acid is going to have the prefix hydro and the suffix ic acid. If the anion is a polyatomic ion that ends in ATE, then the acid is just going to get the ic acid as its suffix.
And those last few rules.
What now, Wagner?
Can you say those last 2 rules that you just said again?
Okay. If the ending of the anion is IDE, then the acid is going to get the prefix hydro and the ending ic acid. If the anion ends in ATE, then the acid is going to get the ending ic acid. And if the anion ends in ITE, then it is going to get the ending us acid. And I am going to illustrate this. So let's look at this one. HCl, Cl has a -1 charge. The acid would be HCl. It has 1 hydrogen because the anion has a -1 charge. Now this anion is called chloride because it ends in IDE. Anything that ends in IDE is going to get the prefix hydro followed by ic acid. So the acid form is going to get the prefix hydro. That underline in the previous section basically is for the root of the nonmetal or the root of the anion. So this is chlor. And then it gets the ending ic acid. This next polyatomic, first of all, its acid is going to be HC2H3O2, where it only gets 1 hydrogen because the anion has only a -1 charge. This anion is called acetate with the ending ATE. Because it has the ending ATE, the acid is going to be the root of the anion followed by ic acid. So this is acetic acid. The next one here is phosphite. It, first of all, the formula, because it's a -3 charge, means that the acid is going to have 3 hydrogens. Now, because the ending is ITE, the new acid is going to be the root of the anion followed by us acid. So since the root of this ion was phosp, then this one is going to be called phosphorus acid. The next one is nitrate. Its acid form is going to be HNO3 with 1 hydrogen. Since the anion ends in ATE, that means that the acid is going to be nitric acid with the ending of ic acid. The last one, the acid form is going to have 2 hydrogens because the anion has a 2- charge. The anion is sulfide. With the ending IDE. Therefore, looking back, that means that we're going to have a prefix of hydro followed by the root. In this case, it's sulfur, and the ending ic acid. So this is hydrosulfuric acid. Now, to finish out these formulas, one of the things that I should have been doing is I should have been stating that they are aqueous, just to separate them from other forms. Everything should have been listed as aqueous. Questions? This finishes up naming. So you have ionic compounds. With the ionic compounds, you have metals whose charge is constant and metals whose charge varies. When you have a metal whose charge varies, you're going to need Roman numerals. And you have covalent molecules. There were 4 categories of covalent molecules that we talked about. Those 4 categories of covalent molecules were the diatomic elements, the hydrogen with group 15 through 17 nonmetals, the alkanes, and the binary covalents. Finally, you have acids. And we talked about how to name an acid and how to develop the formula for an acid. Whether it is a binary acid or whether it is an oxyacid, the process is the same. By the way, just so you know what the definitions are, a binary acid means bi means two. So we're still talking a 2-element acid. So H2S counts, HCl counts. Those are 2-element acids. Whereas an oxyacid is going to be an acid of a polyatomic ion. So if you ever hear that term, you know what they mean. This is a good place to get a cup of coffee or stretch or whatever you need to do. So we will come back at 9:10 and we will pick up with Lewis structures. Okay, it is 9:10, so I'm going to get back to it. We are going to get into the second portion of today, which is going to be Lewis structures. Last Wednesday, I introduced the concept of Lewis structures. We started with the Lewis structure of an atom, of an element. And basically, what we did is we took the elemental symbol, and that elemental symbol not only identified what element it was, but that elemental symbol represented all of the core electrons. Around that elemental symbol, we placed the valence electrons as dots. And the reason we place the valence electrons as dots, it's because those valence electrons are responsible for the element's reactivity. The next thing that we did is we developed the Lewis dot structure for an ionic compound. And in that Lewis dot structure, what was illustrated is the metal lost its valence electrons or transferred its valence electrons to the nonmetal. The number of electrons that the nonmetal gained was the number required to achieve an octet. Now, once the metal lost its electrons, we place that metal in brackets with the charge as a superscript to the right. We did the same thing for the nonmetal. We illustrated that the nonmetal gained those electrons, so it had an octet. That nonmetal was placed in brackets with the charge as a superscript to the right. This is done for all ionic compounds where you place the new electron structure, the new Lewis structure of the cation and the anion in brackets with the charge outside, and then those are simply attracted to one another. After that, we got into the Lewis structure of covalent molecules. I started by illustrating the Lewis structure of 3 diatomic molecules, those being hydrogen, oxygen, and nitrogen. I used those diatomic molecules because I was able to introduce this concept of a single bond, a double bond, and a triple bond. Now, when developing the Lewis structure for covalent molecules, there is a process that can be followed. The first step is to add up all of your valence electrons. And if the substance is a polyatomic ion, then you also take into account the charge when adding up the total valence electrons. Step 2 was to develop the skeletal structure of the substance by placing the central atom in the middle and surrounding it by the external atoms. And I gave you rules to help you determine who the central atom is going to be, but it's typically the first element listed unless that element is hydrogen. Hydrogen is never the central atom. Carbon is always the central atom, but typically the first element listed, unless it's hydrogen, will be your central atom. We then drew a single bond between the external atoms and the central atom, and we subtracted 2 for each bond we drew. If electrons still remained after drawing the bonds, we then gave our external atoms an octet, meaning 8 electrons. The exception to that was hydrogen, which only requires 2, and boron, which only gets 6. But everybody else better have a total of 8 surrounding it. Once we gave our external atom an octet, if electrons still remain, they go on the central atom in pairs. Once you've distributed all of the valence electrons, meaning that that column of mass hits 0, then we determine, does everybody have an octet? Usually, if somebody doesn't have an octet at this point, it's going to be that central atom. So if there is an element that does not have an octet, then we bring in a pair of electrons from the external atom to share with the central atom. And keep in mind, when you hit 0 on that mathematical column, you cannot add any more dots. You cannot add any more lines. All you can do is manipulate what is currently there. So again, we would bring in a pair of electrons to share between the outer atom and the central atom. And we would do this until we achieved an octet for everybody. Now, today, what we're going to do is we're going to continue this process, but we need to bring in a couple of more definitions. We need to talk about an expanded octet, which is going to require us to discuss formal charge. We also need to discuss Lewis structures when there is more than one central atom. So let us begin with the Lewis structures of an expanded octet. Any element in period 3 or greater can have an expanded octet. It can have an expanded octet due to the fact that there is the availability of the D subshell. The D subshell does not have to be filled. It just has to be available, and it can be, you can have an expanded octet. So again, any atom in period 3 or greater can have an expanded octet? When will an expanded octet be necessary? Well, that's based off of its formal charge. So formal charge is calculated as the atom's number of valence electrons. And from that, you're going to subtract 1 for every electron that is a dot, and 1 for every line. We will expand the octet if in doing so, we can reduce that formal charge. We want to get the formal charge as close to 0 as possible. Now, when we're reducing this formal charge, it's important to note that we cannot have the same charge on adjacent atoms, meaning we can't have a negative next to a negative, because if you have a negative next to a negative, just like with two magnets, they're going to repel one another. So as we're doing the formal charge, we cannot have the like formal charges on adjacent atoms. Now, again, we're going to try to get the formal charge as close to 0 as possible. One example where you will not get the formal charge to 0 is if you're dealing with an ion. If you're dealing with an ion, the formal charge is going to be equal to that of the ion's charge. Now, if formal charge must exist, meaning you could not get the formal charge to 0, then if there is negative formal charge, it's going to be on the more electronegative atom. The most electronegative atom on the periodic table is fluorine. The least electronegative atom on the periodic table is francium. So the closer the atom is to fluorine, the more likely it is to have a negative formal charge. I feel like this is going to be easiest if we actually do some examples. Basically, it's impossible to see it until you do some examples. So the first example I want to do is the triiodide ion. Okay, step number 1 is to determine the total valence electrons. We have 3 iodines. Iodine is in group 17. The last digit is a 7, so it has 7 valence electrons for a total of 21 valence electrons. The charge must be taken into account. Because it's a -1 charge, we're going to add 1 for the negative charge. For a total of 22 valence electrons that must be distributed. Step number 2 says to develop the skeletal structure. For this one, we're going to pick one of the iodines to be the central atom around which we're going to surround it with the other 2 iodines. The next step says to draw a single bond between the outer atom and the central atom. And we're going to subtract 2 for each bond we drew. We drew 2 bonds. 2 times 2 is 4. So we're going to subtract out 4 electrons due to our bonds, which gives us a total of 18 valence electrons still to distribute. The next step in the process says to give your outer atoms an octet. To give our outer atoms an octet, they need 6 electrons each. The reason they need 6 is because they currently have 2 in their single bond. So by giving them 6, they achieve an octet. We gave 6 to each of the 2 iodines that were outer atoms. So that is a total of 12 valence electrons that we distributed to our outer atoms. If valence electrons remain, they go on the central atom in pairs. So we're going to place the last 6 on the central atom in pairs. Once you hit 0, you asked, does everybody have an octet? Our iodine on our outer iodines all have 8 valence electrons, 6 within the lone pair and 2 within the double bond or within the single bond. Our central atom has 10 electrons, 4 within the bonds and 6 in the lone pairs. So yes, everybody has an octet. Now, is it acceptable for one of our elements to have more than our central atom to have more than an octet? The answer is yes. It is acceptable for our central atom to have more than an octet. Because our central atom is in period 3 or greater, it can have an expanded octet, meaning it can have more than 8. Now, this is an ion, and all ions are placed in brackets with the charge as a superscript to the right. Now, just for practice, let's calculate the formal charge on our atoms. So let's calculate the formal charge on the outer iodines. I'm listing it once because they look identical. It is going to be the number of valence electrons for an iodine. An iodine has 7 valence electrons because it's in group 17. We will subtract out 1 for every, how did I do it? 1 for every dot on that iodine. There are 6 dots on the outer iodine. And 1 for every bond. There is 1 bond. So therefore, the formal charge on the outer iodines are 0. Now let's look at the formal charge of our inner iodine. The inner iodine is going to have 7 valence electrons, minus 1 for every dot. It has 6 dots, plus 1 for every bond. It has 2 bonds. So it has a minus 1 valent or minus 1 formal charge. So if I were to look at this, the formal charge of these outer atoms is 0. And the formal charge of the inner one is a -1. This makes sense because the sum is a -1, which is equal to the charge on the ion take a moment and look at that. And then ask questions if you have them. Okay, I want to just take a moment to go over this because this brings in a lot of what we did last week with the new piece of information. Now that everybody, I think, has had time to write it down, I want you to listen and follow along as we go through the process. Step number 1 is to determine your total valence electrons. We had 3 iodines. Iodine is in group 17, so each iodine contributes 7 valence electrons for a total of 21 electrons from the iodines. You have to take into account charges when determining your total valence electrons. So we added 1 additional electron due to the charge to our total valence electrons to get 22 valence electrons. Step number 2 said to develop your skeletal structure. In this particular case, all of the atoms were identical, so we just chose one of the elements to be our central atom, around which we placed all other elements. The next step says to draw a single bond between the external atom and the central atom, and to subtract 2 for each bond you drew. We drew 2 bonds. 2 times 2 is 4, so we subtracted out 4 valence electrons for our bonds, leaving us 18 valence electrons still to distribute. According to the rules, if you still have electrons, you next give your external atoms an octet. Each external atom had 2 electrons in the bond, so in order to give them an octet, they needed 6 additional electrons. So we gave 6 electrons to each of the external atoms to give them an octet for a total of 12 electrons that were distributed on the outer atoms. That still left us 6 valence electrons. The next step said that if electrons still remain, They go on the central atom in pairs. And so we place them on the central atom and the last 6 electrons on the central atom in pairs. And that is when we hit 0. When you hit 0, that is when you ask, does everybody have an octet? The external atoms do have an octet because they had 8 valence electrons, 6 in the lone pair and 2 in the bond. Our central atom, however, has 10 valence electrons, 4 within the bonds and 6 within the lone pairs. We then asked ourselves, is that an acceptable thing to do? Can an element have an expanded octet? In this particular case, iodine is allowed to have an expanded octet because it's in period 3 or greater on the periodic table. So the next thing I wanted to do, and then once we had developed that structure, we placed it in brackets with the charge outside because you must do that for every ion. It's placed in brackets with the charge outside. Our next thing I wanted to illustrate is how to calculate the formal charge. When I looked at the structure, I noticed that both of the outer iodines looked identical. So I only calculated 1 round for the external iodines. The formula is, it's the number of valence electrons minus 1 for every dot plus 1 for every bond. So we had 7 valence electrons for the iodine. We subtracted out 1 for every dot. There were 6 dots on the outer iodines and 1 for every bond. There was 1 bond attached to the outer iodine. When you do that math, it comes out equal to 0, which means that our external atoms had a formal charge of 0. We then did the formal charge for the inner iodine. It is, again, the number of valence electrons minus 1 for every dot plus 1 for every bond. Therefore, we had 7 valence electrons for the iodine. We subtracted out 6 due to the lone pairs on the central iodine. And we subtracted out 2 for the 2 bonds on the central iodine, giving it a -1 formal charge. The sum of the formal charge, if you add them all together, is equal to a -1. This is perfectly acceptable because our substance had a -1 charge. And when you have a ion, the formal charges are going to add up to the charge on the ion. So hopefully going through that helped you now that you aren't writing. Let's look at the next one in line. Which is going to be XCOF4. XCOF4 is one of the first molecules for a noble gas. Let's calculate. We have 1 xenon. Xenon is in group 18, so it has 8 valence electrons. We have 1 oxygen. Oxygen's in group 16, so it has 6 valence electrons. And we have 4 fluorine. Fluorine is in group 17, so that's a total of 28 valence electrons. So we have 42 valence electrons to distribute. The next step says in our process is to develop the skeletal structure. Typically, the first element listed is going to be your central atom around which you're going to place all other atoms. We are then to draw a single bond between each of the outer atoms and the central atom. And we subtract 2 for each bond we drew. We drew 5 bonds. 5 times 2 is 10, so we'll subtract out 10 due to our bonds, leaving us 32 left to distribute. The next step says that if there are electrons that still remain, they're placed on the external atoms in pairs. So we're going to give our fluorines 6 additional valence electrons because fluorine currently has 2 in the bond. So in order for it to have an octet, it needs 6 more. And that is true for every single fluorine in the structure. Fluorines, each fluorine got 6, so 6 times 4 is 24, so we'll subtract out 24 there. And that leaves us 8 valence electrons to distribute. Again, you give your outer atoms an octet. Our oxygen currently has 2. To give our oxygen an octet, it needs 6 more. So we'll give out 6 more for our oxygen, and we are left with 2. According to the rules, if electrons still remain once you've given your outer atoms an octet, they go on the central atom in pairs. So we will put this 2 on the xenon and we hit 0. When you hit 0, the first thing you're to ask is, does everybody have an octet? Your fluorines have 8 valence electrons, so yes, they have an octet. Your oxygen has 8 valence electrons, so it also has an octet. And your xenon has 2, 4, 6, 8, 10 within the bonds and 2 in the lone pairs for a total of 12 valence electrons. So yes, everybody has an octet. I was asked, can you put the oxygen on one of the fluorines? And the answer is no. We do not, in this particular case, have 2 central atoms. And also fluorine will only ever have a single bond. It will never have 2 bonds to it. Now, here, your central atom is in period 3 or greater. Any time your central atom is in period 3 or greater, you must do formal charge to determine if you have the correct Lewis structure. One more time. Anytime your element, your central atom, is in period 3 or greater, you must do formal charge to determine if you need to continue expanding the octet. So let's do formal charge. We're going to do formal charge for our fluorines first. Fluorine is in group 17. The last digit is 7, so it has 7 valence electrons. From that, we're going to subtract 1 for every bond. There is 1 bond on the fluorine and 1 for every lone electron. There are 6. So each fluorine has a formal charge of 0. Let's look at the formal charge on oxygen. Oxygen has 6 valence electrons. Because it's in group 16, the last digit is 6. We will subtract out 1 for every bond. It has 1 bond. And 1 for every dot. It has 6 dots. So that means our oxygen has a formal charge of a -1. Finally, let's do the formal charge of our xenon. Xenon is in group 8. The last digit is group 18. The last digit is an 8, so it has 8 valence electrons. We'll subtract out 1 for every dot. It had, or excuse me, 1 for every bond. It has 5 bonds. And it has 2 dots. So currently it has a +1 formal charge. The absolute value of formal charge equals 2. The question is, can we reduce that? So currently, if we go back up here, and we look at the formal charge that we have assigned, each of our fluorines has a formal charge of 0. Our oxygen has a formal charge of a -1, and our fluorine has our xenon has a formal charge of +1. Can we reduce that formal charge? The answer is yes. We can reduce the formal charge by sharing a pair of electrons between the 2 atomic nuclei. The electrons will always come from the element that has the negative formal charge. The electrons will always come from the element that has the negative formal charge. Okay, when we get to that stage, now our structure is this structure. The question is this a better structure? The only way we are going to know if this is a better structure is if the absolute value of formal charge is less than 2. So we calculate our formal charge. Our formal charge on our fluorines has not changed. It is still equal to 0. And that is because we did not alter the fluorine portion of the structure. So what we really need to do is we need to look at the formal charge of our oxygen and of our xenon. The formal charge of oxygen with this new structure is 6 valence electrons minus 1 for every bond. It has 2 bonds plus 1 for every dot. It has 4 dots, meaning that it now has a formal charge of 0. The formal charge on our xenon, it has 8 valence electrons minus 1 for every bond. It now has 6 bonds plus 1 for every dot. It has 2 dots. So the formal charge on our xenon is 0. So the absolute value of formal charge is now equal to 0. So this is is the Lewis structure of XeOF4 because xenon can have an expanded octet and formal charge has been reduced to 0. Questions? Let's look at one more example. And this is going to take into account everything we have discussed about Lewis structures. It is going to take into account the process to develop the Lewis structure. It is going to take into account resonance structures. It is going to take into account formal charge. So it's going to be a complete story, and you have to use all pieces of this puzzle in order to be able to get the correct Lewis structure for sulfate. Okay. Step number 1, determine the number of valence electrons. We have 1 sulfur, we have 4 oxygens. Sulfur's in group 16, the last digit is a 6, so it gives 6 valence electrons. Oxygen is in group 16, the last digit is a 6, so it also has 6 valence electrons. Between the sulfur and the oxygen, that is 30 valence electrons. But you must take into account the charge. It is a -2 charge, so we're going to add 2 due to the charge, for a total of 32 valence electrons that must be distributed throughout our molecule. The next step in the process says to develop your skeletal structure. The first element listed is typically your central atom, so it's going to be the sulfur, around which we're going to place all other elements. You then draw a single bond between the external atom and the central atom, and we're going to subtract 2 for each bond we drew. We drew 4 bonds, 4 times 2 is 8, so we'll subtract out 8 valence electrons due to the bonds. That still gives us 24 valence electrons still to distribute. The next step says to give your external and atoms an octet. Our oxygens currently only have 2 within the single bond. So in order to give them an octet, we must distribute 6 valence electrons to each oxygen atom. 6 times 4 is 24, so we will use up 24 electrons in order to give our outer atoms an octet. And we hit 0. When you hit 0, if you need to alter this structure in any way, you have to manipulate what is there. You cannot give it extra bonds. You cannot give it extra dots. You can only manipulate what is there. When you hit 0, you ask, does everybody have an octet? Your oxygens have 8 valence electrons because they have 6 within the lone pair and 2 within the bond. So that is a total of 8. And your sulfur has 8 valence electrons as well. So yes, everybody has an octet. The question is, should sulfur expand its octet? Although every atom has an octet, the question is, should sulfur expand its octet? Since it's in period 3 or greater. To figure that out, you've got to do formal charge. So let's calculate the formal charge of our oxygens. The oxygen has 6 valence electrons. We're going to subtract 1 for every bond. It has 1 bond and 1 for every lone pair. It has 6 electrons in the lone pairs for a total of a -1 formal charge. So on our oxygens up here, every single one of them has a formal charge of a -1. Let's do the formal charge of our sulfur. It has 6 valence electrons. We're going to subtract out 1 for every bond. There are 4 bonds, and 1 for every dot. There are no dots. So therefore, it's going to have a +2 formal charge. So what we can say is that the absolute value of formal charge equals 6. That's a lot of formal charge. So yes, we have got to manipulate this structure. We have got to reduce this formal charge. So we reduce the formal charge by bringing in a pair of electrons to share between the central atom and the external atom. So we have oxygen. That we brought in a pair of electrons from that top oxygen to share between our central atom and our external atom. Because we altered this structure, we have to calculate the formal charge. The formal charge on the single bonded oxygens is going to equal 6 valence electrons minus 1 for every bond. It has 1 bond. Plus 1 for every dot. It has 6 dots. So that's a total of a -1 formal charge. So our single bonded oxygens still have a -1 formal charge. Our double bonded oxygen is going to be equal to 6 valence electrons minus 1 for every bond. It has 2 bonds plus 1 for every dot. It has 4. So it now has a formal charge equal to 0. And our sulfur is going to be 6 valence electrons minus 1 for every bond. It has 5 bonds plus 1 for every dot. It has no dots, so it now has a +1 formal charge. So what we did by making that one double bond is the absolute value of formal charge now equals 4. So we've reduced it. The question is, can we reduce it further? Well, yes. We can bring in another lone pair. So now we have a double bond sulfur to oxygen on the top and on the bottom, and a single bond on the right and on the left. Because we altered this structure, we now need to calculate the formal charge. So let's do the formal charge for our single bond oxygens. It is 6 valence electrons minus 1 for every bond. It has 1 bond plus 1 for every dot. It has 6 dots. So the single bonded oxygens still have a -1 formal charge. The formal charge on our double bonded oxygens is 6 valence electrons minus 1 for every bond. The double bonds, there's 2, 1 for every dot. There are now 4 for a total of 0. So the formal charge on the double bonded oxygens is equal to 0. Now our sulfur. The formal charge on the sulfur is equal to 6 valence electrons minus 1 for every dot. It has, 1 for every bond. It has 6 bonds, and 1 for every dot. It has 0. So it now has a formal charge of 0 as well. So our new structure has an absolute value of formal charge equal to 2. Now, here is where I'm going to quit on the formal charge. And the reason I'm going to quit on calculating formal charge is because if you will go back to one of the first things I said about formal charge is that with an ion, the formal charge is going to equal the charge on the ion. So if we have a -2 charge on sulfate, that means our formal charge has to equal a -2. So this actually works out that this is, so one of our structures for sulfate has the sulfur single bonded to 2 oxygens on the top and bottom, and double bonded to the 2 oxygens on the top and bottom, and single bonded to the 2 oxygens on the left and right, with a -2 charge. Again, we put it in brackets because it is an ion. But here is where this structure is insufficient. I chose the top and the bottom. There is no reason that the left oxygen and the right oxygen couldn't be my double bond. So therefore, it is a resonance structure. Where the top and bottom is single bonded and the right and left is double bonded. And so this is the structure you would write for sulfate. Questions? Are your heads overflowing? Okay. I originally had thought about starting VSCPR theory today. But if you don't have a grasp on Lewis structures, you can't do VSCPR theory. So what I'd like to do is, instead of doing VSCPR theory today, I would like to introduce VSCPR theory tomorrow in lecture. Which means I have covered as much as I'm going to cover today. I am going to stay on and answer questions, but I think that if I try to introduce VSCPR theory at this point, it's not going to sink in. And VSCPR theory and some of the rest of it that is going to come up is going to be stuff you're going to see in College Chem 2. It's going to be stuff that you'll see in organic chemistry. And so I want to make sure it sinks in. But you got to have Lewis structures to start. So I am going to call it quits for today. I was asked, is there practice for Lewis structures on Blackboard? And yes, there is. I'm pretty certain it's in this week's folder. Other questions? Okay, if not, then I will see you tomorrow for lecture. And this is the last lab lecture for the semester. That will be just a lecture.